Interpolation is very common operation when you do data analysis or when you develop model, because your model could read some observational data set, like say reanalysis of meteorological fields, and you need to, and usually their grid spacing or resolution is very different than your model's resolution. So you need to interpolate your initial, say, data, initial conditions from some observational data set or some reanalysis product. So it's very common that you need to interpolate. So there are various ways of doing so. And usually people don't use very high accuracy of interpolation because there are some problems with that. Basically, the most common method is to fit a polynomial through your data. So if you have a certain number of grid points, you take like 2 or 3 of those neighboring ones, and you try to fit polynomial. And then after you feed it, you have basically some kind of functional form. You can then determine value in a coordinate that you want to, which is not necessarily the same points as your data is, so somewhere in between. So interpolation, the simplest one is, of course, linear interpolation. So first linear. That's the simplest one. So in linear interpolation, so you have 2 grid points, say k and k plus 1. So if you have values of function in that point and this point, k sub k and k plus 1. So you need to find, so this coordinate here is xk and here is xk plus 1. And I'm not using some delta, some constant. Your data may not be necessarily kind of equally spaced. And your data can be pretty arbitrary spaced in general case. So generally you have some point x between 2 grid points, and you want to know what value in that point is. And of course, with linear interpolation, it's almost it's obvious. So you generally just try to find a polynomial of order 1, so it's just linear function, some coefficient, and linear function can be written like the following, x minus, you basically put your virtual coordinate or this kind of moving coordinate 0 in one of the grid points, then your expressions become kind of simpler. So let's choose xk. In that case, your coordinate 0 is x minus xk, so when x equal to xk, it's 0. So that's the easiest one. Plus b. So this is general form of polynomial of first order. So how to find a and b? Of course, you use your known grid points. From that, you have that when x equal to xk, this point, this equals to 0, so your function equals to b. So from that, you immediately get that b equal to fk. And a equals to, from the following, you take second grid point, k plus 1, fk plus 1 equals to a xk plus 1 minus xk plus b, which is fk. So your a becomes simply fk plus 1 minus fk divided by xk plus 1 minus xk. And so now you just use those in places of A and B. And if you write it a little bit more kind of applicable form, you can find that f at point x equals to 1 minus weight, some weight in the point fk, plus weight, the same in the point fk plus 1, such that weight equals to x minus xk divided by xk plus 1 minus xk. So this is weighted interpolation, so it's linear with two weights. So basically, when your x is close to fk, one minus weight becomes very small. So 1 minus weight becomes very close to 1. So you basically becoming more and more like fk, and vice versa. If you move it to fk plus 1, your weight is actually increasing to 1, and then it becomes all value of k plus 1. So, and we use this kind of similar approach when we talk about two-dimensional interpolation, so-called bilinear interpolation. So it's similar observation that this weight kind of it basically, so value in this grid point equals to dimensionless ratio so this weight related to this grid point is actually proportional to weight opposite kind of interval from point x. So weight of this value is actually corresponds to this interval. So this is very important to do, like for example, when you do interpolation of say density on you have staggered grid, and in staggered means that you have say your scalar values in at some height levels, and your vertical velocity levels can be staggered or in between levels. And then you have this problem, okay, I have densities defined in a scalar levels, and now I want to compute densities at vertical velocity levels to compute flux, for example. You cannot just take value at nearest point. That would be only kind of first order accurate, and this one would be more accurate this way. So you need to take this into account, thickness of layers. Of course, it's not the case when you have just equal spacing everywhere. Then it's just arithmetic mean. Okay, so this is linear interpolation, very simple and very common actually. And sometimes when you have just uses the initial conditions or for some comparison to your model results, usually if you have dense enough grid, many grid points and not very, very far spaced, maybe it is sufficient to have just linear interpolation of your data in many cases. But if you want something more accurate, you need to move to the next level, which is parabolic interpolation or quadratic interpolation using parabola. So in that case, you have now, so parabolic interpolation. Quadratic. So it is more accurate, but involves a little bit more computation. So you have now let's say you have 3 data points, and they're not necessarily equally spaced again. So you have, say, call it k minus 1, and k plus 1. And this is your fk minus 1, fk plus 1. So you need to find some value, like for example x here or here, whatever. So you need to find some interpolation formula that goes through all three, for polynomial that go through all 3 points. In that case, it's going to be parabola. So you need to find coefficients for parabola that goes through these points and takes exact values in those nodes or grids or these grid points, exact values of fk minus 1, fk, and fk plus 1. So again, you go, this is your general formula of parabola, and we put our 0 coordinate in the central point. Why not? It's symmetrical kind of. So you have a times x minus xk squared plus b x minus xk plus c. So this is general form of polynomial of second order or parabola. So now from again, immediately if x equals to xk, we have value f equal to fk, so our c immediately is known. That's why it's kind of convenient to write in this form. C equals to fk. So now we need to, in order to find a and b, we need to solve 2 equations with 2 unknowns. And for that, you first use your values in k minus 1, then in value k plus 1. So you have fk equals to a, and now this x minus xk minus, xk minus 1, it's k minus 1 minus xk squared plus or minus b, let's write it this way. And here, because it's squared, it doesn't matter how you will subtract. So let's subtract k minus 1 so that it would be positive distance. Then it's minus b, xk minus 1, and plus fk. This is our c. And fk plus 1 equals to a, xk plus 1 minus xk squared plus b, xk plus 1 minus xk plus fk. So now you need to solve system of 2 equations with 2 unknowns a and b. And it's a little bit tedious if you do it by exclusion, substitution. The easiest is, of course, to use matrix form of this equation, and then just use Kramer's rule that I showed in lecture number 1, when you replace columns of a matrix with your particular right-hand side. This is called Kramer's rule. And that's very cool rule because it allows you to solve equations for particular, if you have even, say, several variables, several unknowns, and you're interested only in one of them, you can actually use Kramer rules to find only that particular variable. But I'm not going to subject you here to, again, writing all these matrices. So maybe I just write how you do it. You just basically write your A and B. So this is, so you have matrix xk minus 1 squared. And then here there is minus xk minus xk minus 1. And here you have xk plus 1 minus xk squared. And here you have xk plus 1 minus xk. And then you have right-hand side AB. I mean, your unknown vector AB, and then its right-hand side, which is also vector, not matrix. It's Fk minus 1 minus Fk, and Fk plus 1 minus Fk. And then you use your Kramer's rule, so you take this column and replace it with this column with right-hand side, and this gives you a value for A, and then you determine you write your as did it in lecture 1. You compute Jacobians, and you compute determinant of a matrix, and you divide by Jacobian, and that gives you A, and then you take the same way with B. And of course it's tedious, so usually nobody does it like this, but I do actually, because I find it easier. For small matrices, of course, I cannot do it with matrix 5 by 5. For that, if you, so you may be wondering, what if I have a system of equation of, say, 5 unknowns or 4 unknowns? And of course, if you're talking about one kind of specific problem, you can go to, say, Python, and there are like functions that compute you that, or some somebody coded them already. So you can actually just use it to solve system of equation. You supply matrix. But what if it's an Fortran program? Of course, you can find look for some online, some library of linear algebra. And one of those libraries that very fast, that optimize for specific hardware, for example. It's a so-called LAPACK library for Fortran. LAPACK library. This is linear algebra. It's an ancient library, so the syntax of calls are very kind of ancient, but it's the fastest solver of any linear equations systems that you can possibly find. I'm pretty sure that inside all your Python scripts and other things, they have this Fortran routine, which is hidden from you, that actually used to compute all this stuff. Because it's been written a long time ago, and by very smart people who actually were very conscious about storage, memory. For example, LAPACK library, when it computes result, your column, it actually replaces your right-hand side. So it's even trying to save storage of arrays, because it was coded back then, those times when memory was storage on a computer was an issue. So, but it's the fastest that you ever can find. Why you need fast? Let's say that you could do this interpolation for 1 billion grid points in your model. In each grid point, you interpolate your data into that point. You do it 1 billion times. Even if you 1 microsecond longer, like you code it yourself by hands, like using Kramer rule or something. 1 microsecond times billion is going to be what? 1 million seconds difference. It will take you 1 million seconds longer. So it's impossible to do something like that. So that's why it's very important to use this kind of LAPACK library. And on Intel processors, it's called like KLM. So it automatically will replace the LAPACK library with even faster library that works specifically for Intel processors. I don't know, some of you know this, but so basically this is what you do. You supply this matrix, and it's not necessarily 2 by 2. You just supply matrix in an array, but you need to be very careful, because in LAPACK, for some unknown reason, matrix, even though in Fortran you probably know that first index is the fastest one. So in Fortran you have matrix A and IJ. In memory it stores, first you change index I, and then J is advanced by 1, then another I is changing, then J advances by 1. In C, for example, it's opposite. So first, like the fastest index actually second than the first. But in Fortran like this, and that's why I don't understand. When you supply matrix A to LaTeX, make sure that you supply it by columns, not by rows, as normal people would do. You will get a completely wrong result because it will work. So basically you take column and you put it in an I index, which is actually a row in Fortran. So it's opposite. I don't know why this is it. It's actually not obvious. I just looked at the example because this LaTeX library comes with example code so that you knew how to use it. And then I noticed that actually it's completely reversed. But if you follow that, it will be like, it solves matrices, say 100 by 100 in a like fraction of a second. But of course, if it's like matrices 1 million by 1 million, it would be very slow. So something else would be needed. So anyway, so if you solve this using like by hand, of course, I'm not advising to use LaTeX because LaTeX just solves it for actual numbers here. But this is what, if you solve it by hand, you will get the following result, that A equals to 1 over xk plus 1 minus xk minus 1. And here you have fk plus 1 minus fk divided by delta by xk plus 1 minus xk. So it's very kind of symmetrical. And here you have minus fk minus fk minus 1 divided by fk x, sorry, xk plus 1 minus xk. K plus 1 is xk minus, sorry, xk minus k minus 1, yeah. So, and there is actually a very good reason why it should look like that. Actually, you could find A without even solving this, if you actually, and that we're going to talk about next. And B equals to a little bit more tedious, xk minus xk minus 1 divided by xk plus 1 minus xk minus 1. So it's basically, let me write in the same, sorry, in the same form. It actually looks like the same. And here you have this interpolation formula for the linear that we used, kind of looking kind of similar. It's fk plus 1 minus fk. Yeah, here it should be multiplied by xk. Sorry. No, I thought that it's easier. No, it cannot be already than that. So it's basically the same interpolation formula for linear interpolation, we just average of it. Fk minus xk minus 1 divided by xk plus 1 minus fk times fk plus 1 minus fk and plus xk plus 1 minus xk divided by xk plus 1 minus xk minus 1. And here is fk minus fk minus 1 divided by xk minus xk minus 1. Oh, actually, I already wrote it. Yeah. So here is just weights. It's basically the same as we used for linear interpolation. It's just 1 minus weight times weight.
I have a question. So at the denominator, at the b is x k plus
A
1.
plus 1 minus xk minus 1.
Yeah. On the right side of that, is it x k plus 1 minus fk or xk?
Ah, yeah, that's a good point. It's xk minus 1. Yeah. So the same.
The one above.
Xk minus sk minus 1, xk plus, no, this is correct.
No, denominator.
This one?
The
This
right one.
This one?
Yeah. Is it f or xk? Is that f?
Oh, sorry. Yes, x. Yeah, of course.
Thank you.
So this is a little bit tedious process, but if you coded it, it will spit out your interpolation right away using like any x when you substitute it in there. But of course, and this one will work with any arbitrary grid. And but of course, what if you're looking for some high order interpolation? So high order interpolation or general interpolation that you have, if you have, so you have f I point from I equal to 1 to n. So this is your observations. And then you have, of course, coordinates the same way. Then in general, your ends, you can, your in polynomial that goes through all the endpoints should be, would have n plus 1 coefficients. So it's like this polynomial is called L, or okay, Y, polynomial of order n equals of x equals to a plus b x plus c x squared and so on. Or if you actually use all a's, so it's a0 plus a1 x plus a2 x squared plus and so on a n x to the power of n. So in order to fit through n data points, this is, well, we use this capital N, let's use small n. You need nth order polynomial, and with linear or quadratic interpolation, that's not a problem. But of course, if you want to say you want a more accurate interpolation, like say using 4 or 5 grid points, you may need would be very difficult to inverse your matrix. So basically, this looks like matrix, right? This is equation. So in grid points y in these nodes, the right-hand side would be your values of f at xi's. So you have matrix that consists of these a's. I mean, the a's are your vector, and matrix will consist of 1, x, x squared, and so on for these values, and second row is like for second, and so on. So we'll have this n by n plus 1 times n plus 1 matrix. And then you need to use, say, LAPACK package to inverse it. But of course, nobody does that, because there is actually better way. So I just gave it to you for kind of as an example. But there is so-called, fortunately for us, this very famous mathematician Lagrange has come up with very simple formula for polynomials that fit through arbitrary number of grid points. So, and it's called Lagrange formula. That's very easy to code. So Lagrange polynomial. So Lagrange, I would say it's formal or more than. So that's very simple. That Lagrange polynomial would be given by the following: y of x. Say you have again this n number of data points and n coordinates and n values. So you need to come up with some value of polynomial that goes through all these grid points and in some arbitrary x, which is inside that total interval where your data is defined. Because if it's outside, it's not interpolation, it's called extrapolation, right? And extrapolation, you could still use that same formula if it's not very far away. And in fact, you can, like, sometimes people use extrapolation based on, especially if it's time series, you can basically extrapolate the future a little bit, maybe some glimpse. But normal extrapolation is not good thing. Like in numerical methods, if you derive some derivative and use extrapolation, not interpolation, usually those methods are unstable, so they usually blow up. So extrapolation is not a good thing, but interpolation is a good thing. So Lagrange polynomial written like the following: it's a sum. So this is Lagrange polynomial of order n. So it means that you have n grid points. So now you need to find value at any point x. So you have I equals from 0 to n. So this is sum. And here you take grid point I, so let's put this from 1. This one is using like C language. And this one is n plus 1. So you have grid point I, so you have n grid points. So you have x minus x 1 times so on x minus xi minus 1. So you're not taking this x that equals to 1. You skip it. xi plus 1 and times so on x minus xn. And you divide it by x I minus x1 and so on, xi minus xi minus 1. So you see there is symmetry here. And xi minus xi plus 1 and so on, and x minus I minus xn. That's why you skip xi, so that you won't divide by 0, right? So this is a little bit tedious, but it's just basically what you do, you have these data points and you have coordinates and you want to find in this coordinate, and it will give you a result right away if you, well, it's easy to code in Fortran and just a bunch of loops. For example, actually, I think it should be from 0. Yeah. So you start counting your data. You have n plus 1 data starting index from 0. It's like C convention. Yeah, otherwise it won't work. Yeah, it should be from 0. Okay, so let's take an example. How actually does it work or not? So example, let's say that n equal to 1. So this is first order polynomial or linear interpolation. So we have y1 of x, or let's call it like 1, equals, so take first I equal to 0, y 0, times x minus x1, and that's it, because n equals to 1. We finished already. So it's divided by this, guys, which is also, it's just x0 minus x1, plus y1, so next data point, x minus x0 divided by x in this case 1, so x1 minus x x0, the same, and that's it. And you can, it looks kind of weird, but it's actually the same interpolation formula that we got before, just written a little bit differently. So here you have 0, you replace by xk, and 1 you replace by xk plus 1, and you get the same formula. So but you see, it's of course, it doesn't matter how you generate interpolation polynomial. There are actually other methods, like there is Newton polynomial. There is Hermite polynomial. They all produce the same coefficients, just using different methods of computing those coefficients. Because there is only one and only one polynomial you can fit to a certain number of grid points. Like if you have n, it's n grid points. So you need, like you have, say, 2 points, it's polynomial of order of 1. So it's n minus 1 power of polynomial. So if you have some, say, 10 grid points, your polynomial will be 9th power, maximum, biggest power of x. So and it's unique. It's guaranteed to be unique. So all this, but there is a danger. Well, just for completeness, maybe I leave it as an exercise. Maybe, right? It's like for parabola, but it's much easier in a way than solving all these Kramer rules, matrices for parabola, right? This is just mindless application of this algorithm. It doesn't mean that this one is faster, because lots of multiplications, then if there is division, and division is very bad thing. But in Kramer's rule also there is division, so maybe it's not that bad. Division, why division is bad, maybe I mentioned it before, certain microchips, RISC chips, for example, not Intel so much. They don't like division, it's very long operation compared to multiplication. It can be like up to more than 10 times longer than multiplication. So you need to avoid it. Okay, so there is a danger though if you have so-called overfitting, because you have like some grid points and all this. So your polynomial may go like that. And maybe this is not what you want. Like see here, maybe by I it should go something like that. But if you actually use actual fit of polynomial, it may be some weird function, especially when it's a high order polynomial. So I would highly discourage using high order polynomials for interpolation. You may get, and in homework, I think I will get some example when higher order polynomial gives you actually a wrong result and smaller worse accuracy than, I mean, in physical sense error, not mathematical sense. Because physics cares about this stuff. And if you have like polynomials that, because you use very high order polynomial, you get all these wiggles, so that you know, what polynomial tries to do is just to go through all these grid points. It doesn't care what's happening in between. So you may have, when you fit very high order polynomial, this kind of wiggles around like between the points, which is not physical at all. and it may produce you some problems. Like, for example, if it's temperature, it could be like when you interpolate on your higher resolution grid, you may get some weird spikes in temperature. So my advice to you, if you interpolate data for your model, use linear or maximum parabolic interpolation, quadratic. Don't use higher order. You may get otherwise some artifacts. Usually quadratic doesn't produce too much of artifacts, pretty tight kind of fitting to only three grid points. The linear, the beauty of linear is that it won't produce you any new maxima and any new minima in your data. That's the beauty of it, right? Because it's always weighted mean between two grid points. It cannot produce like, artificial spikes. But high order polynomials can very easily do that. And you may, if you say interpolate some nightly data set, you may get like at some points, like instead of 10 degrees Celsius, you may have like 15 degrees Celsius just artificially because of polynomial fitting, which may not be a very good thing. Okay, so also before moving on with interpolation, so for interpolation, basically my advice to you use linear and quadratic. Quadratic if you have to, and usually linear, if you have dense enough data set, it should be sufficient. Avoid high order polynomials at all costs. They produce sometimes very unexpected results. So bilinear interpolation. So what if it's 2D data set? And I will talk only about bilinear. There is also equivalent of quadratic, but it's much more, you can imagine, tedious to describe. So bilinear or interpolation is very common and very popular because it's basically very simple and very easy to code if you need to code it yourself. So basically the idea is the following. So you have some grid cell and you have your data points here, say F, I, J. So this is indices going I and J. So in this direction it's going I, in this direction it's going J. So I'm trying to use actual indices so that you kind of used to that, because not like F1, F2, just to make it kind of more, if you're designing the code so that you already have your indices for your arrays. So it's I plus 1J, here is Fij plus 1, here Fi plus 1, J plus 1. So very common. So this is your data, say, from reanalysis. And your grid is much, say, higher resolution. And this is very important. Interpolation works nicely if you interpolate and then from coarse grid to finer grid, not opposite. If you interpolate from finer grid to coarse grid, all sorts of artifacts can be produced. And you understand why, right? Like if you have, say, some function and you have very fine grid, and now you trying to interpolate to coarse grid, then if you interpolate from fine grid to the coarse, you take these points like here and here. So it's pretty, and then you say that the whole, this big cell is filled by this big value. But in reality, you need to first kind of smooth your data before you interpolate to coarse grid. So you take your high resolution data and you kind of run some first running mean to make it like kind of not the spiky, but more like your coarse grid. Because otherwise you may get your coarse grid has very kind of arbitrary large values that come from this, just by accident, by this high resolution data. Let's say you interpolate into 100-kilometer grid, and then some data points that lies right at the interpolation grid point can be like some lake in winter. And it has like 0 degrees Celsius temperature because it's water. But around it's minus 20 degrees Celsius surface. And your air temperature is, say, also close to minus 20 Celsius. And now you have this interpolated value, which is temperature difference is 20 degrees Celsius from surface to your first grid point in your model in the atmosphere, just by chance, because you got it. And then it will create you like 5,000 watts per meter square flux when you compute it. And it will blow up your model probably if you're not careful enough. And you don't understand. Everything works fine. I just interpolated another data set and everything blows up. What happened? And then you start like analyzing. It's just because you interpolated this lake, which is kind of tiny, just accidentally from high resolution data set to your coarser model. So that's why when you interpolate from coarse to fine, not opposite. Okay, so just a little piece of advice. Now, you have, let's say, some grid point here. This is your fine grid point. So there are many of them. So you take one at a time. So its coordinates are, you defined a grid such that your x coordinate here, and this is 0, and this is y. So you normalize it. You say that x equal, and actual coordinates can be like x, y, these coordinates are x, I, j, and so on, xi plus I, j, and y, x, y plus 1, j, and so on. So you normalize them by these distances so that your coordinates from 0 to 1, that's just convenient. So it becomes like ones. So now you have coordinates, this point with coordinates x, y. So what's valued based on these values? You use just weight, weights the same way as for linear interpolation. So basically the geometrical interpretation is the following. So this value contributes to value here as which box? This or that? This or that? Or that? This one. This is your weight. So this point for ij. This is for point I plus 1j. This is for point ij plus 1. And this for point I plus 1, j plus 1. So you see it's completely opposite. And it's obvious because if you point very close to this grid point, weight is probably the whole square, right? So this is because it becomes like this value here. So it's opposite. So the general formula that f at coordinates x and y equals to this weight, which equals to, what's this weight? To this grid point, Fij times weight, which is this guy. So it's 1 minus x, 1 minus y, divided by 1, which is the whole area, so we don't even write it. Plus Fi plus 1j times, so it's this grid point, so it is this guy. So it's x times x times 1 minus y plus Fij plus 1. It's this ij plus 1. Yes, this one. It's 1 minus x times, so it's this weight. Hold on, I kind of, x, sorry, that's what confused. Oh no, it's this point, oh sorry, this point, so it's this guy, so it's 1 minus x times y, yes. And plus Fa plus 1, j plus 1, just x times y. That's it. So It's very easy. It's very easy to organize in a loop. So what you do, first you compute your coordinates of your fine grid that you want to interpolate from this data. You take these coordinates and find the guy that just barely has that actually has x coordinate just smaller than your x, and y coordinate just smaller than y. So you find this guy. Then you take data points, if it's regular grid, next ones. So it produces you this. So you need to search for it. And that's why this interpolation procedure can be very slow, because it's search involved of this initial coordinate here. Unless it's so regular that you can predict it, like if it's like constant stepping, then you can actually compute it very easily. But what if it's like arbitrarily spaced data? I mean, not arbitrary, but not very, the stepping is not constant. Then you need to search it kind of in general. But if you found, then you normalize these coordinates and you normalize your x and y coordinates. So x is just your actual coordinate minus this coordinate. This is your x divided by this distance. It becomes from 0 to 1. And then use this formula. I do it in my model when I interpolate from era 5 data to model grid and global grid. And it works very fast. So you don't need to prepare your data set. First, I try to actually interpolate my data set first for global model, and then read it when my model runs. So offline, first prepare data sets and read it from the model. And it turned out that in order to run five-day simulation on a grid, which is like 4-kilometer grid spacing, so it's like 3 billion grid points, it would take me to interpolate my data set to hourly, to run it as kind of nudge to observe data set. So basically I need like hourly data sets. And then I computed that in order to interpolate it offline, it would take me about 3 months to interpolate only 5 days. 3 months. Why? Because it's serial operation. It runs on one processor. And I said, why I do that? Why not my model, which runs, say, on 10,000 processors? Why each processor computes its own data on this small subdomain? And now it takes about 1/10 of a second to interpolate instead of like 3 months. And so that's why it's very important how you approach always these problems of interpolation of data. Do you interpolate offline, or you rather use your original data and interpolate it while model is running? And sometimes the difference can be very substantial, very like not just 10 times, it can be like 1,000 times or so. So it's very important how you do it. I know that some models read data sets specifically prepared for this resolution. Say, it all works if you use, say, several hundred grid points in one site. That's fine. Say, climate models, they probably fine with that. But when you run, say, cloud resolving model on very large domains, say, United States or global even, that becomes unacceptable. You cannot do that. You need to prepare data while model is running so that each little processor, each little subdomain will produce its own data. Okay, so what else about interpolation? I think that's about it. Do you have questions on that material?